In this video, I'm going to talk about AC analysis of MOSFET. So here is the given data and given circuit. So input is connected to the gate and output is connected to the drain. So this is the drain, here is the source. Now, while doing AC analysis, I clearly mentioned to you, if the source or emitter, one of them is grounded while doing AC analysis. That means if there is a capacitor right here, if I have a capacitor and grounded, while doing AC analysis, this capacitor is going to act like a short circuit. So we can say that is AC grounded. Since here we do not have AC ground, we're going to do the T model. If it is AC grounded, then you can do the T model as well as pi model. Pi model is a lot easier. So if you can solve it by using pi model, use the pi model. If you don't want to do pi model, you can solve it by using T model all the time. But this particular example, we have to do it by using the T model because the source is source is not grounded, not drained. My apology. Source is not grounded while doing AC analysis. Okay, so that's about the T model and pi model. Definitely you will get this data Kn prime times width over length, Vt threshold voltage, and Va. I believe I gave you Va too. Sometimes Va instead of Va you will get lambda. Va is nothing but 1 over lambda. Now we're going to do the DC analysis first. So while doing DC analysis, remove all the AC sources and remove the output. So we want to figure out whether this transistor is in active mode of operation, triode mode of operation, or triode mode of operation. So we always know this gate current is 0 no matter what. Okay, and the voltage at this point is, since there is no current passing through this, okay, the voltage at this point Vg must be equal to 2 volts, whatever the supply voltage here. Since there is no voltage drop, the voltage at that point is going to 2 volts. Now we're going to solve the circuit by assuming saturation mode of operation. So this transistor is going to work in either saturation mode or triode mode. So I'm going to assume this is in saturation mode, and in saturation mode, this is the equation for the current. Okay, and VGS is nothing but Vg minus Vs. So we know Vg, which is 2 volts, Vs is, I know the current here is ID, the same current is go through that is also ID. So I can say Vs equal to, or Vs minus 0, because the voltage here is 0, Vs minus 0 equal to 4K times ID. So that's what I used, Vs. Vs is nothing but 4K times ID. If I take ID in milliampere, so kilo milli get cancelled out, so 2 minus 4 ID. So I substituted the values. Kn prime width over length is given 0.8, and I substituted the values. I found out ID equal to this equation, 0.4 multiplied by 1 plus 16 ID square minus 8 ID. So it's a quadratic equation. So I have 6.4 ID square minus 4.2 ID plus 0.4 equal to 0. So once I have this quadratic equation, end up with two values. One is ID equal to 0.541 milliampere, ID equal to 0.115 milliampere. So substituted ID value to find Vs, I found Vs equal to 2.164 volt and Vd equal to 1.836 volt. Now to be in saturation mode, okay, you're saying your Vd is, the voltage at this point is 1.863, voltage at this point is 2.16, and you're saying current is flowing from drain to source. Is it possible? Remember, current always flows from higher potential to lower potential. I have source has higher potential, drain has lower potential. So definitely this may not be the right current. And at the same time, if you found VGD, you end up with the VGD equal to 0.164. To be in active mode of operation, your VGD must be less than or equal to Vt, threshold voltage. So this is not the right current. So I found the another one, substituted ID, another current. Since quadratic equation, we end up with two currents, right? So I'm taking the second current. substituted find Vs, found Vd, VDS, we end up with 3 volts. So see, drain has higher potential, source has lower potential. So this is true. The current can flow from drain to the source and end up with VGD equal to minus 1.459 minus 1.459 volt. So VGD is less than VT, so it is in saturation mode. This is a complete DC analysis. Here is the AC analysis circuit. So since source is not grounded while doing AC analysis, we have to use T model. So that's what this is, the T model equivalent circuit. So the T model equivalent circuit is, so here is my gate, drain, and the source. So this is the T model equivalent circuit of MOSFET. So this is the T model equivalent circuit of the MOSFET. Now we need to include the remaining components. So we included the remaining components. So here is the RG resistance connected to the gate, and this is the internal resistance of the source and V source. Now these are the input terminals. So the gate terminal as well as the ground is the input terminal, and output terminal is drain as well as the ground is the output terminal. The load is connected at the output terminal, so we put them back. So this is 1 over GM transconductance. The formula for GM is square root of 2 times Kn prime width over length times ID. We already found ID value in the previous video, so I used that in the previous in the DC analysis. So we end up with ID is 0.115 milliampere. So I used that current and found the GM. Now R0 is the internal resistance between the source and the drain. If any one of them are grounded or both of them are grounded while doing a DC analysis, my apology, while doing AC analysis. So if either source or drain, any one of them are grounded while doing AC analysis, or both of them are grounded while doing AC analysis, which is most likely not going to happen because you need to have one of them as output or input, input node or output node. So, but one of them can be grounded. In this case, either my drain is not grounded or my source is not grounded. So we don't need to use the R0. Okay, but this is the formula for R0. So in this case, we're not using R0. We don't need to worry about the R0. Now, the input resistance is resistance between the input terminals. So when we looked at it, input terminals, remember the gate current is 0 all the time. So none of this resistance connected to the source or drain will transfer to the gate. So whatever we look at the circuit from here, that's the resistance, input resistance. My R input resistance between these two terminals is only 50 kilo ohm. Okay, or another way of saying it is, you can connect a test voltage source and see where all the current is going in. So when I connect a test voltage, all the current is going into this 50 kilo ohm. So I see only 50 kilo ohm resistance as the input resistance. Same thing here, my output resistance is, when I'm doing output resistance, I shouldn't have any input source voltage. So my VGS is going to be 0. So this value becomes 0. So when I looked at my output terminals, my output resistance R out is going to be only 4 kilo ohm in this case. Okay, when we're finding output resistance, you shouldn't include the load resistance because this is the output resistance of the total whole circuit. So based on that resistance, maybe you may want to vary the load resistance. And if you look at the Thevenin theorem, remember, if the internal resistance is equal to the load resistance, you will transfer the maximum power. So if that is the condition, you can have load resistance equivalent to output resistance to get the maximum power. Now our goal is finding the gain. Gain is nothing but output voltage over input voltage. This is AV with load. Okay, so when I write an equation at the output voltage, I will end up with V output equal to These two resistors are in parallel. RD and RL are in parallel. RD parallel with RL, and the current passing through them is GM times VGS. Whatever the current coming out, that's GM times VGS. So current is basically entering from the ground. Okay, so this must be minus, so minus GM times VGS. Now our goal is finding the relation between output voltage and input voltage. I know output voltage. Here I have VGS. I need to convert that into VN. So if you look at here, the voltage, even though the current passing through this is 0 milliampere, the voltage here is V input. So basically the materials we are using here make the voltage appear at this point as the input voltage. So if this voltage is total input voltage, based on this I can define VGS by using the voltage division rule. So my VGS must be total voltage V in times same resistance 2331 ohms divided by total resistance 2331 plus 4000. This value is 0.368 VN. So VGS I can replace it with 0.368 VN. So V naught equal to 4K parallel with 4K, which will be 2K, times minus GM. We just found that GM here. GM equal to 0.429 milliampere per volt square, I believe. So if I substitute that here, minus 0.429 milli, and VN or VGS as 0.368 VN. So when I multiply all of it, this is 2K, 2000, and here is milli. Kilo and milli get cancelled out. We'll end up with minus 0.315 VN. So V naught by VN, which is AV, equal to minus 0.315 volt per volt. This is the gain. When it comes to the no load gain, AV naught, that indicates the no load gain. So when it comes to the no load gain, remove the load. So when I remove this becomes almost double. So that value is, all you're going to have 4K times minus 0.429 milli times 0.368 times, VN is already included there. So this value is negative 0.631 volt per volt. This is AV naught. Now overall gain GV equal to AV times RN over RN plus R signal. So here the input has signal resistance of 20 kilo ohm and input resistance is 50 kilo ohm. So there will be significant amount of voltage drop there. So AV equal to, my R input is 50 kilo ohm, AV times, 50K plus 70K. So this value becomes, 50K plus 20K, so it's 50 over 70 times AV. So this value is AV times 50 over 70 is nothing but 0.714. So 0.714 times minus 0.315. So this value is minus 0.315. So this is minus 0.225 volt per volt. This is the overall gain. Now we can draw the waveforms. Now here are the waveforms. So say if the input voltage is 100 millivolt sine omega t. Is that given? I didn't mention it here in this video, but assume that that's the input voltage, 100 millivolt sine omega t. Then our output voltage, our AV, if you remember, it is minus 0.315, right? So you will end up with, if I multiply with 100, it's going to be 31.5 millivolt, and it's a negative, so it's inverted. So your output is going to be inverted, and that value is varies between 31.5 millivolt, negative 31.5 millivolt. That's the output with the gain. Now, if we use the DC voltage, so the output is connected to the drain. The drain voltage we found 3.45 volt. So 3.45 plus, if I take that as a millivolts, it's a 0.0315 volt, right? Since this is milli, if I convert it into volt, it's 0.0315. So here VD is 3.451 plus, I mean, it varies from 3.45 plus 0.0315, that's the voltage there. Here 3.45 minus 0.0315 volts there. Sorry, this is the wrong value. Okay, so these are the waveforms. Sometimes you may get, you may ask whether do I need to use GV there or AV. It doesn't matter for me, you can use any one of those. I prefer you to use the GV, but here in this video I used AV. Okay, I'll stop this video here. Probably I'll make a few more videos in the future. Thank you.